smallest subspace. So the easiest way for me to explain this is, let me just try again, subspace. Okay, so let's say you have this vector space V, and inside V you have these subsets S, T and U. So you have checked that S does span V, T does not span V, and U also does not span V. Okay, so since S span V, S is actually the smallest subspace that you have inside here. Alright, okay, so we have this proof here. This proof here actually goes back to the same definition that we have before in order for you to prove subspace. So you will have to go through the close under addition and also close under scalar multiplication. Where is it? Alright, okay. So let's move on. Okay, so these are some exercises here. So with these exercises here, determine whether the set S spans R2 or R3. So I'm emphasizing again, by now you should know what is R2 and what is R3. R2 means 2 coordinates, for example, this one here. And R3 means you have 3 coordinates, okay, 4, 7, 3. Alright, so this is your question for quiz 2. I want you to submit it to me by tomorrow morning. Alright? Okay, so now we're going to move on to basis. So remember, at the beginning of the lecture, I have explained to you, we are going to learn about linear independence and we are also going to learn about spanning sets. Why we are going to learn these two things? Because we are going to use these two definitions here to form the basis of a vector, which is now we're going to have a look. Because we already know what is linearly independence and we already know what is span. So now we're going to have a look at the basis and also dimension of the vector spaces. Okay, back to the concept of vector spaces. You still remember, right? What is vector spaces? Vector spaces must satisfy 10 properties. 10 properties are divided into 2. Addition and also scalar multiplication. So this addition you have 5 and this one also you have 5. So then only if the vector space given to you satisfy all these 10 properties, then only it is known as vector space. Alright. Okay, so in this section we will continue our study on spanning sets. So this is the basis. Basis is the combination of span and also linearly independent. Remember, okay, linearly independent. Okay, definition. A set of vectors S in vector space V. You see the diagram is the same diagram we are dealing with. Okay. This is the vector space V. And then you also have this one here, which is your S. So S is known, so inside S you have V1, V2, V3 and so on. Right? So a set of vector S, this one here, in vector space V is said to form a basis for V if it satisfies these two conditions. First is S spans V and the second one is S are linearly independent. Okay, so this is the definition of basis. 2 properties that need to be satisfied, which is span and also being linearly independent. All right. Okay. This definition doesn't imply that every vector space has a basis consisting of a finite number of vectors. Okay, some vector space does not have a basis. Why does not have a basis? Maybe the subsets doesn't span, or maybe because it cannot form a linearly independent. It depends. It depends on the question. Okay. Moreover, if a vector space V has a basis consisting of a finite number of vectors, then V is finite dimensional. Okay. The vector space V equals to the 0 vector is finite dimensional. The vector space P of all polynomials is infinite dimensional. Okay, what is finite and infinite dimensional? Finite and infinite here goes back to the same concept. Finite is something that you can count. Something can be counted. Whereas infinite is something that you cannot count. Okay, like this. Okay. So that's why this one here, vector space V equals to 0, has only one vector 0 alone inside, right? Means you can count, or there's only one element inside. So it is finite dimensional. Whereas vector space P of all polynomials, there are so many polynomials, x plus 1, x plus 2, x plus 3, x squared plus x plus 1, and so on. There are so many polynomials. So for that reason, the vector space P is known as infinite dimensional. Okay? Alright, so these are some characterization of a basis. So let S be V1, V2 until Vk. We go back to the same diagram here. Be a set of vectors in a vector space V. The following statements are equivalent. S is a basis for V. Let's say S is a basis for V. S is a minimal spanning set for V. This S here is a minimal spanning set for V. Why? This one actually goes back to the definition that we had a look before this. This one here. Smallest subspace. Smallest subspace here implies minimal. There you go. Minimal spanning. Right? And the third one is maximal. S is maximal linearly independent subset of V. So these three statements are equivalent. Alright? So let's have a look at one example here. Examples are good to illustrate the concept that you are learning. Okay, so you have vectors E1 and also E2. And it says that E1 and E2 form a basis for R2. Why? Let's have a look. Example 1. So you have E1 equals to 1, 0. Okay. And then you have E2 equals to 0, 1. And it says that, let's say this one here is your S. Okay. It says that this S form a basis for R2. Okay. Why? So if you know, we go back to the concept of basis. How many things we need to check for basis? Two things we need to check. One is, we need to check if it's span. The other one is, we need to check if it is linearly independent. Okay. So let's have a look at this one here. Okay, let me just sketch. First, I want to check for span. Okay, so for span, we want to check, so what is our vector space? Okay, so this is our vector space, V2. This is our V, and these are our S. Alright? So now, from V, we want to take some vectors, let's say A1, A2, any vectors from V, from the bigger vector space here. Alright? Let's say A1, A2 sits here. Alright? Okay, and then from S, we have only two choices. We have 1, 0, and also we have 0, 1. Okay? Okay, so now, the thing is that, back to the concept of span, if we can write this vector A1, A2 as a linear combination of the vectors in S, then we can say that S spans V. Okay, so now we need to find out if it's possible. So V is equals to A1, A2 equals to, we're going to have to introduce two scalars because we have two vectors in S. So let's say you want C1, 1, 0 plus with C2, 0, 1. Okay, so let me just continue it at the back. So let me just rewrite. So I have here A1, A2 equals to C1 of 1, 0 plus C2 of 0, 1. Okay, so how do you simplify the right hand side? You're going to get C1 as the first coordinate, and then the second coordinate is going to be 0 plus C2. Okay, so you can see that C1 is going to be equals to A1. Okay, from the first coordinate, you get C1 is equals to A1. And from the second coordinate, you will get C2 is equals to A2. So you see, the scalars exist because A1 and A2 are any vectors from V. Alright? So in this S here, you have 0, 1 and also 1, 0. And from here just now, you have A1, A2. Can be any vectors, A1, A2. Okay? For example, if A1, A2 are any vectors, this is R, we are dealing with R2. Okay, this is your vector space. Let's say you have 4, 5. Okay, so this is going to be your A1, this is going to be your A2. So this one here are going to be C1 equals to 4, C2 equals to 5. You see, the scalars exist. So if the scalar exists, it means that for any A1, A2 inside R2 here, you can write as a linear combination like this. Okay? So it means that S spans R2. Okay? So the spanning part is done. So the second thing that you need to check is linearly independent. Do you still remember how to check for linearly independent? Where's the slide? Okay, there you go. The second slide, this part here. Linearly independent, it means that if you write like this, equals to 0, you will get all the scalars C1, C2 until C3, until Cn are equals to 0. Okay, so let's check if you're going to get that or not. Okay, so how many C1, C2, Cn we have? We only have 2. So we have C1, E1 plus C2, E2 equals to 0. Alright, so what is C1? So 0 in R2. 0 in R2 is equals to 0, 0. Right, 2 coordinates because R2. Okay, C1, what is E1? E1 is 1, 0 plus C2, E2. E2 is 0, 1. And that is equals to 0, 0 on the right hand side. Let's simplify this. C1 plus 0, okay. Second coordinate is going to be 0 plus C2 is equals to 0, 0. Okay, so if you see this one, C1 is equals to 0. C2 is also equals to 0. Okay, so from here, you can see that this one satisfies the linearly independence. So you can say that E1 and E2 are linearly independent. Okay, so when you go through the, what does the question wants you to show? The question wants you to show that if S spans R2 or not, okay, because the V now here is equals to R2. And you know, sorry, not spans, if we want to check that if this S here is a basis of R2 or not. So to check for basis, we need to check two things, span and also linearly independent. You have checked for span, and it turns out that yes, S spans R2, good. And then you check for linearly independent, yes, E1 and E2 are linearly independent, okay? So since both of these characteristics are satisfied, you can make the big conclusion now that S forms a basis for R2. So make sure when you do calculation or proving something like this, make sure to always write the conclusion. Okay, after one section, write the conclusion. Another section, write down the conclusion, and then write down the big conclusion. All right? Okay, so let's have a look at one more example here. Okay. So show that the following set is a basis for R3. Now this R3 is your V. Alright, and this is your set S. So it goes back to the same diagram. Alright, the only difference now is that in this S here now, we have three vectors. Okay, we have this one, and also this one. Alright, and then instead of R2 now, we are working with R3. Okay, it's the same diagram, same concept, only the questions are different. Okay, so the same thing here now. To find basis, there are two things that you need to check. You need to check if it's span, and also you need to check if it is linearly independent. Okay, so to check for span, this is the calculation that I've done here. I write down A1, A2, A3, which is any vector that comes from R3 here. Okay, equals to B multiplied with the first vector in S plus C multiplied with the second vector in S plus D multiplied with the third vector in S. So B, C, and D are my scalars. Okay, so if I solve this by simplifying the right hand side, and also by comparing the first coordinate with the first coordinate, second with the second one, third with the third one, I get that A1 is equals to B, A2 is equals to C, and A3 is equals to D. So you see, the scalar B, C, D exists. because A1, A2 and A3 are any numbers, are any vectors that come from R3. If in R3 we choose 4, 3, 5, B is going to be 4, C is going to be 3, D is going to be 5. You see, the scalar value exists. So since the scalar value exists, so it means that you can write any vector in V here as a linear combination of vectors in S. Because remember, this part is V part. This part here is S part. Alright? So now if we can make a conclusion that set S spans V. So we have checked the first property, the first characteristic. The second one is we need to check about the linearly independent. Okay, so for the linearly independent part, you can see that so this is the one, the linearly independent part. Okay, so you're going to write down C1 multiply with the first vector in S, plus C2 multiply with the second vector in S, plus C3 multiply with the third vector in S, and that is equals to the 0 vector. Okay, the 0 vector in R3. So it's given by 0, 0, 0. Okay, so if you simplify this and you compare left hand side and the right hand side, you will get that B is 0, C is 0, D is 0. So all scalars are equals to 0. So for that reason, it is linearly independent. Okay, this is the second conclusion. So first conclusion plus with second conclusion, you can make the big conclusion that it is a basis. Okay, so the proper conclusion here is S forms a basis for R3. Alright? Okay, so that's good. So now I believe you know what is linearly independence, how to find, and I believe you know what is span and how to find span, and you also now can combine the knowledge that you have about span and also linearly independence to find your basis. Alright? Okay, so let's move on here. Okay, I'm going to have to skip this example 3 because I don't like examples that doesn't explain how you get the answers. You see, there's a statement here and there's only one line of solution. This is not the solution. This is supposed to be not example 3 but exercise 3 because the solution is not given. Okay, so for that reason I'm going to just skip this one here and let's have a look at example 4. Okay, so example 4 is the same question. Okay, show that the set S where V1, V2 and V3 is given by this is a basis for R3. Same diagram again. You have this big V here, which is your vector space, which in this example, the vector space V is given by R3. Okay, so this one here is your R3, right? And then you also have inside here the set S. So inside S, you have V1, V2, V3. The question wants you to check if this S here is a basis for R3. Okay, and you know, again, that to check basis, there are two things that you need to check. First, you need to check for span, and the second thing is you need to check for linearly independence. Okay? Okay, so let's move on with the span. If you see the span part, you pick any vector from R3. Let's say you have A1, A2, A3. So this is the A vector, okay, which is equals to A1, A2, A3. Can be any vector inside this R3 here. And it is equals to x1, v1 plus x2, v2 plus x3, v3, sorry. So x1, x2 and x3 are scalars, okay? S are scalars. v1, v2 and v3 are vectors that comes from this S, set S here. Alright? So now we want to check. For it to become a span, this vector A here, which is this one, must be able to be written as a combination of v1, v2, v3. Means that what? Means this x1, x2 and x3 must exist. Okay, so from here, you can write it down like this. So you just replace v1 with this vector, v2 with this vector, v3 with this vector here. So from here, you can compare left hand side with the right hand side. You will have that a1 is equals to x1 plus x3. x1 plus x3 here because the x2 part is 0. And this a2, the middle coordinate, the second coordinate is equals to x2 plus 2x3 because this part is 0. And also a3 is equals to x1 because this is 0, x2 part is 0, x3 part is also 0. Okay, so what is this? This is system of linear equation. Am I right? So how many types of method do you know to solve system of linear equation? By substitution, Gauss elimination and also by using Cramer's rule, right? But in this case, I think the best choice for you to use is substitution. Why? Because from the third row, you already get the answer for one of the variable, which is x1 is equals to a3. Okay, now you can do a back substitution and get the answer for x2 and also x3. All right. So since you are able to find what is x1, what is x2 and x3, so x1, x2, x3 exist means that not all of them are equals to 0. So you can say that any vector in R3, which is this a1, a2, a3 here, can be represented as a linear combination of the set S. So if it can be represented by a linear combination of this set S here, it means that it is span. Okay, so let me just write down a proper conclusion here. S spans, what's the vector space we are working with here? R3. S spans R3. Okay, so the first conclusion is done. Now we need to check the second conclusion, okay, the linearly independence part. So now you're going to have to write y1 v1 plus y2 v2 plus y3 v3 equals to 0. So this 0 here, we are dealing with R3, so you can write it as 0, 0, 0. Okay, and this y1, y2, y3 are scalars. y1, y2, y3 are scalars. I usually personally like to use scalars to be alphabets like A, B, C, D. Okay, so that it is easy for us to distinguish between if we are working with vectors or we are working with scalars. All right. So in this case here, I actually prefer to write it as A v1 plus B v2 plus C v3 equals to 0. Okay, so now you can easily see that okay, A, B, C are scalars. v1, v2, v3 are vectors, right? Okay, so this one is equal to 0, 0, 0. Okay, so what's next? So there's the same thing. You're going to have to expand the left hand side and compare to the coordinates on the right hand side, and you will get this y1 plus y3 equals to 0, y2 plus 2y3 equals to 0, and y1 equals to 0. Okay, so I think the best method for us to use here again is the back substitution, because one of the scalar is already given by 0. If you solve for second scalar, it's also 0. Third scalar is also 0. So all scalars are 0. It implies that linearly independent. Okay, so you have proof for the span part.